Part 3. We will start or rather continue looking at some more basic topics involved in modeling systems. And these topics are all taught in different areas. You already know them. Some of them are taught in mechanics. Some of them are taught in advanced calculus. Some of them are taught in high school, final year. But by and large, they all integrate to give you the basic skills for modeling. When you look at a system on the outside, you will find that there are two types of systems. One is a system in which once you give the control action, you pretty much forget about what's happening because the output is going to happen without any interference from your side, nor will you know what the output is. The second is a system where once you apply the input, you sample the output to know its condition, and then you compare that output to your specification of what is required at the input level. And by comparing the two, you generate an error signal or a corrective action so that the system is guided back to where you want it to be. The first one is called open loop system. The second one is called closed loop system. Open loop systems are systems where very limited control action is used. Limited in one sense. It is limited in the sense the control action is fixed and it is not changed. Whereas we are aware of what is happening inside the system. We know the system. After all, we designed it. We know the system, but we know nothing of the output because the output is not being monitored. Normally, open loop systems are where potential for damage is very low, and they are also where a human operator is present and he provides the feedback control by watching the output, taking corrective action as and when required. A typical example is the ceiling fan example that we looked at in earlier lectures. Closed loop systems are cases where the consequence of the output is and can be quite expensive. It is also a compulsory requirement in self-monitoring systems, that is, systems that correct themselves back to the correct path. It's also the situation where the quality of the output is very important. Earlier, we talked about system analysis, system design, system identification, and all that, the three parts of systems. Well, when one knows the input and the system has no knowledge of the output, that's called system analysis. You analyze the output. When one knows the input and the output but knows nothing of the system, it's called system design. When you know the system, you know the output, but you have no clue about the input that you need to give, that is called control system. Inputs are the first things that concern us when we look at system design or system identification. Typically, rather surprisingly, the number of inputs that we have in systems that we deal with in everyday life are pretty limited number. For instance, at home, either you switch the light on or off. Either you switch the air conditioner on or off. Either you switch the fan on or off. Whether you switch the water pump on or off. Either the refrigerator comes on or comes off. So these are all what I would call digital input signals. That is, they are status representative and they simply tell you whether something is on or off. So it's very easy to model off as a 0 value and on as a 1 value. And so you have a unit step function which more than meets the demand. It is 0 at all times before t, and at t it becomes 1. This shows you how a signal remains 0 until it reaches a specific time t, and after that it becomes 1. This is called a unit step function. It has a magnitude of 1. Now, the other type of signals that we come across in systems is when you're analyzing things like pumps, vehicles like motorcycle, car, anywhere where a motor is involved. The input action is cyclic, that is, it rotates. Since it rotates, a sinusoidal function serves the purpose quite well. F sine omega t tells you. Omega gives you the frequency of rotation or the RPM, and F tells you the magnitude. The third type we come is a steadily increasing or a steadily decreasing control action. Normally, like anything in real life, they have a limit above which or below which they may not go. So a volume control on your stereo is such a control action where it keeps increasing until it reaches the maximum and it stays there. Even the regulator on your ceiling fan is such an action. The dimmer on your light switch is such an action. We have so far looked at the input signals and how they can be modeled mathematically. The next in our sequence of understanding is the system itself, because this is what processes the input to produce the output or the response. Solution to differential equations is no longer a sophisticated high-level ability as was seen, say, 40, 50 years ago. It is now a compulsory skill for all engineers, and it is something that should be obtained at a fairly early level. Solutions to equations up to third order differential equations is an essential aspect of an engineer's life if he decides to go into some form of systems design. Typically, solutions to differential equations have certain patterns to them. One can look at a differential equation and see whether it has a zero on the right or a non-zero term on the right. That tells you whether the situation is going to be solved by a homogeneous equation or with a particular integral. Either case, it would be very easy if one looks at the equation, one can easily guess the solution, or rather make an intelligent guess at a solution. For instance, something that has only a second order differential implies that you will need something like a sine or a cos, because only they reproduce themselves with a negative sign after they are differentiated twice. There are hints such as this which one learns by experience. Assuredly, sitting down and solving many differential equations for practice, particularly by using books such as Shom's series on differential equations, is a worthwhile skill. If any of you require the Shom series book, let me know. I have a PDF copy. I will give it to you. Let's look at a simple problem to see if we can model the situation. A body of mass m is falling vertically down. It could be anything like a spherical ball that you drop from a height, or a football that you drop from a height, or anything. What is happening to this body? Well, there are two forces that are acting on the body. One is its own weight, and the other is the air resistance or drag. Typically, air resistance or drag, better known as damping because it acts against the direction of motion, is given as a proportional term proportional to the velocity with which the movement takes place. So if you model this as is shown in the slide, a simple free body diagram that shows the weight acting vertically down and the drag opposing the weight. Apply Newton's law where we are looking at sum of external forces equal to mass into acceleration, and you get the problem modeled in a very simple two-step exercise. This is a first-order differential equation because it has first-order derivatives with respect to time. The first solution to such an equation is to assume that a drag is insignificant or zero. That is, the constant of proportionality is zero. This is true particularly in the case of small objects. This gives you dv by dt is equal to the gravitational acceleration, which can easily be integrated to get the position at any time. The second solution is as given in the slide. You can use the initial conditions. You can give it an initial velocity, and you can solve it and integrate it to its solution. Such problems and their solutions are highly condition dependent. These are known as boundary condition problems, and they are dependent on their initial condition. In this case, the initial conditions are defining the solution. The direction of motion, positive velocity, has to be down for the solution. Air resistance or drag has to be proportional to the velocity. As long as these two conditions are met, the solution is valid. Second problem. Let's look at the reverse of what we saw just now. A body is being thrown up directly. That is, it's got two forces acting on it. One is its weight vertically down, and in this case, the drag or air resistance is also acting vertically down. So the equation of motion, by just writing the balance of forces, is given as dv by dt plus k over m into v equal to minus g. The problem has been modeled. In order to successfully formulate the model, one of the most fundamental skills is to represent the system of forces acting on the model. That's easily done by using a free body diagram or FBD, and the balance of forces will give you the equations of motion when you apply Newton's laws with it. Once that is done, the system is successfully modeled. However, many of us, for whatever reason, mostly poor comprehension is the reason, many of us don't understand how to draw a proper free body diagram. And in the process of drawing the free body diagram, we make more mistakes. I would suggest as an alternative method to free body diagram the calculation of determination of Lagrangian. Lagrangian is defined as T minus V, where T is the kinetic energy of the system and V is the potential energy of the system. The difference between the two gives you Lagrangian. There are many methods to model the motion of a system, Newton's laws, conservation of energy, and so on. Lagrangian is another one which is based on the combination of kinetic energy and potential energy. And the equation, Lagrangian equation, is given on the slide right now. The question is, how do we apply this? Let's take a sample problem of a spring and a mass. The kinetic energy at some point x is 1/2 mv squared, where v is dx by dt. The only potential energy there at that instant in time, if you define the origin to be seated on the center of mass, is v is equal to 1/2 kx squared. So the Lagrangian L is t minus v, which is 1/2 mv squared minus 1/2 kx squared. We determine the Lagrangian derivatives with respect to x dot and x, and the equation is readily obtained. Mx double dot plus kx equal to 0, which is the equation of motion for a freely oscillating springs mass system. Again, let's take a look at one of the older problems we already solved once, and that is the falling body problem. The falling body problem at any height x, kinetic energy is 1/2 mv squared, where v is dx by dt. Potential energy is mgx. Non-conservative force is minus kV, where K is the drag coefficient of proportionality. So given these things, L is equal to T minus V, and you apply the Euler-Lagrange equation, one gets the equation of motion. The problem is easily modeled. Just now we looked at a falling body problem. Let's look at the opposite of it, which is the body being thrown up against gravity. As homework, why don't you try to derive the equation of motion for the system by estimating its kinetic energy and potential energy at some point x and at some time t. The correct answer has already been determined in one of the earliest lectures. So in this system, there are references that have to be looked at. And as these lectures go by, the references are starting to pile up. I am not going to upload any more lectures this week. So I would strongly urge you to use this 1 week gap to study these books. Those of you who don't have these books, please drop a line to me on my email ID, which is given at the bottom left hand side of the slide, and I will be able to provide you with the book. I can set up the book on Google Drive on a read-only basis so that you can access it. The course as such, the core of the course as such, is being modeled after the book Mathematical Systems Theory by Olster and van der Voort and Marx and Jalsima. It's an excellent book which will provide you with a very strong foundation in system modeling. Frank L. Severance is a similar book but slightly more advanced. Thank you.